Hi class, this lecture continues Chapter 4. We're talking about forces and motion. We talked about describing motion with velocity, acceleration, position, and then we talked about Newton's laws and the three laws of motion, and we've discussed a little bit the law of gravity. We'll talk about that a little bit more, but in this part we want to talk about what are called conservation laws, things that are conserved. It means that there are certain things that don't change. So what are these things that don't change, and when are you sure that they don't change? So we talked about momentum before, so what we're going to be looking at is why do objects move at constant velocity if no force acts on them? That has to do with momentum. And then we also mentioned angular momentum. So a question that you might ask is what keeps a planet rotating and orbiting the sun? That comes from an idea called conservation of angular momentum. And then where do objects get their energy? There's a conservation of energy law. And these are very fundamental laws of nature, more fundamental really than Newton's laws. So these conservation laws are very important. So momentum, if you remember, is mass times velocity. And it turns out, if you do experiments, you can verify this, that if you have, say, a collision, you've got two objects. We refer to these two objects, these two balls, as your system. And in this particular system, these two balls are going to collide, and there's a force of interaction between the objects within the system. So these two objects interact with each other. And if there are no outside forces, if there are no external forces, or if all the external forces cancel out, then what happens to be true is that the total momentum of the system does not change. And so what that means is that this ball comes along with a certain mass and a certain velocity. This ball doesn't have any velocity, so it doesn't have any momentum. When this collision occurs, as long as no external forces are acting on the system, are influencing the motion of the objects, then all that's going on are internal forces. And what they do is they serve to transfer momentum from one object to another, but the total momentum remains the same. And so you might see this when you play billiards. You'll see one ball heading directly toward another ball, and this ball that's moving after the collision will sit still, while the ball that got hit will move with the same speed as the ball that was coming in originally. So there's a perfect transfer of momentum from one ball to the other. Now technically, there's a little bit of sound. You'll hear a little bit of sound in that collision, so there is a little bit of energy loss. All right, so energy of motion might not be conserved. Energy in total is conserved. There's energy of motion as well as sound energy in this case because you hear the collision, but momentum is still conserved. So momentum is transferred from one ball to another. The total momentum of the system doesn't change. And so this ball that was stationary moves along then with the same velocity as this moving ball had. And this moving ball that was moving ends up having the same velocity that the second ball had, which is 0 after the collision. So when objects interact, and you can ignore external forces, either there aren't any or they cancel out. And an example of canceling out external forces is these balls right now, they're resting on a surface. And so the surface itself is pushing up on each ball, kind of up out of the screen here. And gravity, though, is pulling down. Because the balls are not moving up and down relative to the surface, they're only moving along the surface. Those up and down forces, that normal force and gravity, cancel each other out. Those are two external forces, but they cancel each other out. So as long as external forces cancel out or they don't exist, then momentum of the whole system doesn't change. But the individual parts of the system may change their momentum when the objects interact with each other. So then the sun and the earth, why does the earth keep going around the sun? Well, there's something called angular momentum. And a rough formula for angular momentum, it's not as simple as just mass times velocity, and it's not as simple as this equation. It's a little more complicated, but when the earth is in this position in its orbit, it is a certain distance r away from the sun, and when its velocity is moving perpendicular to that radial distance, the angular momentum can be written as mass times velocity times radius times distance. When Earth is in a different place, the angular momentum is written slightly differently, but the amount that you measure, the amount that you calculate, is the same. So there's an idea of conservation of angular momentum. This quantity, mass times velocity times radius or times distance, doesn't change, even though you might calculate it slightly differently at different points. The quantity that you calculate is still the same number. And the reason for this then is because there are no external torques acting on the system. And a torque is like a twisting force, a force that causes something to turn or to rotate or to move around in a circle or an orbit or something. So as long as there's no outside torques, then the system's angular momentum does not change. And so the Earth will continue to go around in its orbit. If there was some kind of a torque, which could come from, if the Earth was moving through some really thick debris, let's say, out in space, air, suppose there was air out in space, then you'd have air resistance as the Earth moved, and that would provide a torque, that would provide an external torque that would slow the Earth down, and eventually the Earth's orbit would spiral down into the sun, and that wouldn't be very fun. So angular momentum is conserved, mass times velocity times distance, because there's no external, no outside torques or twisting forces acting on the system. So conservation of angular momentum, again, is that angular momentum doesn't change, and it's mass times velocity times radius. And the outside torques are what causes changes in angular momentum. So the Earth and the Sun don't experience any of these outside forces. At least they're very minimal. And technically there are interactions of the Earth and the Sun with other planets in the solar system. So technically, and the Moon as well, really the Moon is a little more important. So technically there are some outside forces. And so technically the Earth's orbit might be changing a little bit over time, but it's kind of negligible. It is certainly something we would take into account if we wanted to look at how the Earth's motion around the Sun would change over thousands and thousands of years. But certainly over even 100 years, that those motions, those outside torques are very weak, very negligible. So there are some things. But if you look at the solar system overall, look at the whole solar system overall, all the objects that go around the Sun have some total angular momentum. And really, what's interacting with the solar system as a whole is extremely weak. The nearest star is about 4 light years away, and so it's very, the outside torques, the outside forces are very, very, very tiny. They might exist, but they're so small we can easily ignore them. So the overall angular momentum of the solar system is certainly very conserved, even though the Earth-Sun angular momentum might be, to a good approximation, conserved, but technically over a few thousand years, things do change a little bit. An example of angular momentum conservation is seen in an ice skater when she spins on her skates on an axis that runs through her body. When she holds her arms out, she'll spin at a certain rate. When she brings her arm in, there's some total angular momentum when she spins. And that's going to be constant as long as there's no external forces acting on her, and there's very little friction between her skates and the ice. When she brings her arm in, she changes what's called her moment of inertia. She changes her radius, in a sense. She changes how the mass is distributed or away from the axis of rotation. That's what this R is kind of representing. Technically, for her, the angular momentum is not just mass times velocity times radius. It's a little more complicated. But there is a quantity that's like radius, like distance, that depends on how the mass is distributed away from the axis of rotation. So if she starts off with her arms sticking out like this and she gets herself spinning, she establishes a certain amount of angular momentum. And that amount isn't going to change. But if she brings her arm in, she effectively is making the radius smaller. And her mass doesn't change. So her velocity then changes. It's really a rotational velocity that changes. So she speeds up. So as the radius gets smaller, the velocity gets bigger. And technically it's angular velocity that we would talk about, which is, these are terms that we can focus on more if we were taking a more formal astronomy course, a more formal physics course. But there's something related to speed, and in this case it's speed of rotation that would increase. So energy. So we talked about conservation of regular momentum, conservation of angular momentum. Now we want to talk about energy. What is energy? Where does it come from? When is it conserved? How is it conserved? And so on. So types of energy that you might hear about are kinetic energy. Kinetic energy is energy of motion. The faster you move, the more kinetic energy you have. It's related to the mass and the speed. Radiative energy is light, basically just the energy of light. Infrared light, you feel when you put your hand near a candle off to the side, you'll feel radiative energy. You'll feel the infrared light from the candle warming up your hand. If you put your hand above a candle, you feel that radiative energy, but you also feel energy of the hot air rising up to meet your hand. So that's actually kind of more like kinetic energy. The hot air coming up and hitting your hand, and those air molecules being hotter, moving faster, interacting with your skin. We'll talk about heat in a moment. And then there's potential energy, which is stored energy, and there's various forms of stored energy. Chemical potential energy in gasoline. When you fill up your tank, you put gasoline in your tank. There are chemicals in there, and your engine burns those chemicals, converts that potential energy ultimately into kinetic energy of your car. But not all of the energy in the gasoline goes into energy of motion of the car. Some of it's wasted. So there's always some waste. It's very hard to be 100% efficient in converting one form of energy into another form of energy. But we can convert energy from various forms. So thermal energy is a form of kinetic energy at kind of the macroscopic scale. So when you think about a gas or a solid or something like that, the gas and the solid, they're all made of molecules, atoms and molecules. And an object that has a certain temperature, we say has a certain amount of thermal energy. It has a certain temperature, but it has also a certain amount of energy. Temperature and energy are not the same thing. What temperature measures is like the average kinetic energy of the particles that make up a substance. So if this is a gas at low temperature, the molecules are moving at a certain speed on average. Some are moving slower, some are moving faster, but the average kinetic energy is a certain value, and that's related to the temperature. As I increase the temperature, I increase the average motion of these particles. They move around faster on average. Again, some could be moving slower, some could be moving faster, but on average they're moving at a higher kinetic energy, and therefore the substance has a higher temperature. And then thermal energy is of course related to the temperature, but it's related also more toward the material as well, how much material there is, what type of material it is, and so on. Here we have some temperature scales. Think about the Fahrenheit scale for a second. Water freezes at 32 Fahrenheit, water boils at 212. So suppose you have a pot of boiling water at 212 degrees Fahrenheit, and it's on your stove. And you also have your oven that is also at 212 Fahrenheit, let's say. That's actually a pretty low temperature to cook something at, right? You might cook something more at 350 or 450 or something like that. But suppose your oven is at 212, and so is the pot of boiling water. They both have the atoms and molecules in those substances within the oven and within the pot of water have the same average kinetic energy. They're moving on average with the same kinetic energy. Well, which one would you want to stick your hand into? I wouldn't want to stick my hand into the pot of boiling water, but sticking your hand into a 212 degree oven is not that difficult at all. You could stick it in there, it wouldn't burn right away. You could probably hold it in there for several minutes even. It might start to get fairly warm, but as long as you don't touch the sides of the oven, you'd probably be fine. So the difference between the oven at 212 Fahrenheit and the pot of water at 212 Fahrenheit is the thermal energy content of those substances. Water is more dense. There's a lot more atoms and molecules moving around at that same kinetic energy, average kinetic energy. And so there's a lot more things that are interacting with your hand to transfer energy to your hand when you stick your hand in the pot of boiling water. There's a lot fewer atoms and molecules flying around inside the oven. The air is much less dense than the water. So when you stick your hand in the oven, many fewer particles interact with your hand, transferring energy to your hand. And so your hand doesn't absorb as much thermal energy when you stick it in the oven as it would when you stick it in a pot of boiling water. So things can have the same temperature. They can have very different thermal energies. And again, the thermal energies depend on the content, the density of the material, the type of molecules that make it up, and so on. So these are the different temperature scales that we'll talk about. We'll talk about Kelvin quite a bit because that's the scientific scale that we will use. The Celsius scale is often used in Europe. We use Fahrenheit here in the United States. And Celsius is in fact is used in many places around the world, but we can convert between the two. The Kelvin scale is very similar to the Celsius scale. The changes in Celsius, if you go from 0 to 100 Celsius, you also change by 100 Kelvin. So an amount of 1 degree Celsius is the same as an amount of 1 Kelvin in terms of a change in temperature. But the 0 for Kelvin is often called absolute 0. It's the coldest you can get, basically. That happens to be negative 273.15 degrees Celsius. Now, absolute 0 doesn't mean that everything's stationary. Some people say this, and you might hear this being mentioned in places. It doesn't mean that everything is totally frozen and nothing absolutely moves. That's not what it means. Absolute zero means that you've taken out as much energy as you can possibly take out of a substance. Everything is down to its lowest energy state, we call it. To understand this, we really have to talk about quantum mechanics, and that's not something we'll do too much of in this class. A little bit. Not in any formal way, though. We'll talk about some of the concepts. But there's a concept in quantum mechanics called zero-point energy. It's the lowest energy that an object, a system, can have. And so at 0 Kelvin, everything in the system is at its lowest possible energy. But that's not zero energy. There's still some motion. There's still some lowest energy kind of motion there. So 0 Kelvin is the lowest energy at which you can extract any more energy. You've extracted everything you can possibly take out. So here's the pot of boiling water again in the oven. And again, they have an oven here at 400 degrees Fahrenheit. But if we are, 400 Fahrenheit versus 212. But even if the temperatures, were the same, I think it's better to compare them with the same temperatures. Then you can easily compare. Yeah, you could stick your hand in that oven at 212, and it would be, wouldn't be affected much at all. You could keep it in there for a while. And again, that's because there are many fewer particles inside this oven. The particles inside the pot of boiling water are much more dense, even though they're all moving around with the same average kinetic energy. In this figure here, though, you see the arrows are a little bit longer on these guys because the temperature is higher, 400 degrees instead of 212. So these guys have a little bit higher average kinetic energy. But still, you could stick your hand in an oven of 400 degrees. As long as you don't touch the walls or the metal grates or anything like that, your hand could stay in there for, 10, 20 seconds, no problem probably. But certainly not in the pot of boiling water. That would not be good. Gravitational potential energy is a form of energy that's stored. And we'll talk about this when we talk about the formation of the solar system and the formation of stars. If you throw a ball up in the air, it goes up to some maximum height. And as it's going up to that maximum height, it's slowing down. Where is that kinetic energy going? So it's losing kinetic energy as it goes up. And then as it falls, it's gaining kinetic energy back. Where does that kinetic energy come from? So where does it go on the way up? Where does it come from on the way down? What we say it goes into and it comes from gravitational potential energy. As an object goes higher and higher, the mass doesn't change, the strength of gravity doesn't necessarily change, although it could, but the distance that the object could fall changes. The higher and higher you go up, the greater and greater potential there is for the object to come back down and travel at a higher speed when it lands. So gravitational potential energy has to do with the mass of the object in particular, that's up there, and also the mass of the Earth. The mass of the Earth is incorporated in little g, the acceleration due to gravity. So the gravitational potential energy depends on the mass of the object, the strength of gravity, and the distance that it is above the Earth, let's say, or the distance that it is above whatever it's being attracted to, which could be other particles, as we'll see when we talk about planet formation and star formation. And so the higher you throw something, as it goes up and up and up, the more gravitational potential energy there is, and that potential energy comes from the loss of kinetic energy. So there's an example of energy being conserved. You have some total energy, kinetic plus potential. That total energy doesn't change, but you change the forms of the energy. As the object goes up, you lose kinetic energy. It gets transformed into potential energy. And then when the object reaches its maximum height, that potential energy gets transformed back into kinetic energy as the object falls and moves faster and faster and faster. So the total energy doesn't change, but there's a transformation. Now this, of course, is technically only true if we ignore air resistance. Air resistance does take energy away, and energy of motion, let's say. It does take kinetic energy away, and it doesn't really give it back. So if there was air resistance, this total of kinetic plus potential would actually decrease, because the air resistance would take some of that energy away. But if we can ignore air resistance, if we did this on the moon, for example, or out in space, well, not out in space, but on a planet that doesn't have any atmosphere, then if we throw a ball up with a certain kinetic energy, it would go to a certain height, and it would then ultimately come back down. And during that time, we could measure the potential energy and the kinetic energy at any point along its path, and we would find that the total is always the same. It's just that we switch forms from one to the other. Here's an example showing the collapse of a cloud of gas in space. And we'll talk about this later on in a future chapter. But there's these clouds of gas out in space, and they're just atoms and molecules moving around, and they're attracted to each other by the gravitational force. They also could be attracted to each other by electromagnetic forces. They could be repelled from one another by electromagnetic forces as well. But gravity is always attractive. So if some kind of a disturbance comes through here, like some kind of a shock wave from an exploding star somewhere else, you could get little pieces of the gas and dust to start kind of clustering. And once you have little pieces kind of clustering, then more pieces start to get attracted. And so you'll have this situation where more and more little pieces, more and more little atoms get attracted to other little atoms. And as they get closer to each other, they start speeding up. You get a conversion of gravitational potential energy into kinetic energy. The atoms and molecules start moving faster and faster. The whole cloud starts collapsing, starts contracting. Ultimately, it forms a disk. And we'll talk about why that is later, but ultimately it forms a disk, a flattened disk. And it gets very, very hot in the center because of all this conversion of gravitational energy into kinetic energy. And again, kinetic energy at the atomic level is something we might think of as thermal energy, which is kind of measured, and sort of an aspect of it at least is measured by the temperature. So the temperature increases in this central region, and really the whole thing, the whole cloud, the temperature increases as it collapses and the objects speed up as they convert gravitational potential energy into kinetic energy. Another form of potential energy is mass energy, energy stored in the mass of an object itself. This is something that Einstein showed was true, and this has been verified many times in many ways. And nuclear explosions, nuclear reactors, and things like that are examples of the incredible amount of energy that you can get from a very small amount of mass. So you convert a very tiny amount of mass into pure energy. You can get an incredible amount of energy. Conservation of energy basically says that if you think about all these different forms of energy and you have some kind of a system that isn't interacting with anything, all right, so you've got this system, and the energy in the system takes different forms: kinetic energy, potential energy, mass energy, thermal energy, whatever the different chemical energy. You can't create energy or destroy energy out of nothing. So that total energy in the system is always going to be some number, some constant number. But it can change forms it can go between those different forms. So the total energy of the system doesn't change, but the forms of energy can change within the system. If you have something from the outside interacting with the system, then you can get the total energy of the system to change. If something pushes on the system or puts energy into the system, the total energy can increase. If something takes energy out somehow, the total energy of the system can decrease. So an isolated system has the same total energy. But again, that energy can take different forms within the system. So what have we learned? We've learned that there's this idea of conservation of momentum, and that says that if there's no total external force acting on a system, or the total forces cancel out, then the total momentum does not change. Then there's conservation of angular momentum, and that involves twisting forces. If there's no external twisting forces, then the total angular momentum doesn't change. Angular momentum is conserved. And then with energy, if you have an isolated system, energy isn't just created or destroyed within it. Energy can change forms within it. And so if the system is isolated, you can't increase or decrease the total energy of that system. So let me show you a couple things that you might be interested in looking at. In the study area of Mastering Astronomy, there's a couple tutorials, self-guided tutorials here. These are good. The gravity and the motion and gravity one is one that would be good to go through. It talks about gravity and general ideas of motion, forces, Newton's laws and force of gravity and so on. It's a good one to look at. The energy tutorial is also a good one. This is a really good one to look at. This is talks about all these things that we've just been talking about: kinetic energy and gravitational potential energy and other forms of energy and so on. So I'd highly recommend that you go through these self-guided tutorials. And then there's another website. If you Google PHET interactive simulations, or just Google PHET, there are some good interactive simulations that are created by the University of Colorado through a grant. And these are Java. So they're Java based, so you have to make sure your computer system's updated, and download the Java application, and you can run it. So I'm running one right now that's on gases and properties of gases. So in this little thing, what you do is you can choose whether you have like a heavy type of atom or molecule or a light type of atom or molecule. We'll just keep it at heavy. And it's an empty container right now, and you're going to be able to control a couple things. You can control the heat source right there. If you turn this on, oops, you got to slide this guy up. You can heat it up, or you can cool it down. Ice cubes come up or flames come up. You can take this guy over here and you can push on the chamber and change the volume, right? You can change the volume of this chamber in here. This is going to measure the temperature of the gas in the chamber, and here's a lid that you can remove. Let things escape. So you first have to put gas in there. So you hold this little handle and you pump gas into the chamber. Let's give it a couple pumps. And so you can see, after things kind of established themselves, there's a lot of collisions happening. And, you know, some little guys are moving faster than others. Little atoms and molecules moving faster, some are moving slower. There's kind of a, you know, random motion, very random motion in here. There's some average kinetic energy, and that's indicated by the temperature, 300 Kelvin. And there's a pressure. There's some pressure in here, 0.5453 atmospheres of pressure. All right. So you can change some things. What happens if I heat up the system? What happens if I add thermal energy to the system? Well, I do that by putting a flame under the chamber here. So let me heat up the system. You can see the temperature going up. All right, let it go. So now the temperature is up to 433. And you might notice that the atoms and molecules are moving around now a little bit more rapidly. So keep an eye on these guys moving around, and let's heat it up some more. Here comes some more heat. Can you see how much faster they're now moving? Things are zipping around really fast, really fast, as I'm increasing the temperature up there, up to almost 2000 Kelvin. The temperature is going really high. Now, I could try to go really even higher in temperature and watch what happens. Let's see if we can do this. Oops, do it here. Keep increasing the temperature, increasing that. There goes the pressure. The pressure's going up, it's going up, it's going up. Oh, and pop, the lid flies off, and that's a pressure cooker with a lid that popped off. And now the gas is escaping. So the atoms are escaping simply by traveling straight out of that opening. They don't necessarily all go out, but the ones that are heading up toward the top can escape because there's no top on there anymore. And as fewer and fewer atoms are in here now, the temperature goes down. They're slowing down as they collide with each other. They kind of, the hot ones sort of fly away. The fast-moving ones kind of fly away, and what you're left with are the slower-moving ones, and that's indicated then by a cooler temperature. So let's put that lid back on and pump some more gas in there. So we put some gas in there, and we've got some temperature, we've got some pressure, and it's going up a little bit. It'll come to what we call an equilibrium. You can also see what happens when I change the volume. So I decrease the volume. Decreasing the volume, squishing the gas like this, makes it wiggle around a lot faster. There's less volume for these guys to move around in. The temperature actually goes up. So there's all kinds of interesting properties of gases that you can talk about when you change the pressure, change the volume, change the temperature. But the main thing we want to focus on here is that the average motion, the average kinetic energy of these guys is indicated by the temperature. The higher the temperature, the more rapidly they're moving around. So I hope this helps understand some of these concepts of energy and motion, and specifically those three big conservation laws: conservation of momentum, conservation of energy, and conservation of angular momentum. Those are all things that we'll see more of in the future.